Our next speaker is Michael Snyder, who is going to be speaking on managing and extending health. And you go ahead and get your computer set up. Michael Snyder is the Stanford Asherman Professor and Chair of Genetics and the Director of the Center of Genomics and Personalized Medicine. He is a leader in the field of functional genomics and proteomics, and one of the major participants of the ENCODE project. His laboratory study was the first to perform a large-scale functional genomics project in any organism and has developed many technologies in genomics and proteomics. These including the development of proteome chips, high-resolution tilling arrays for the entire human genome, methods for global mapping and transcription factor binding sites, paired and sequencing for mapping of structural variation in eukaryotes, de novo genome sequencing of genomes using high-throughput technologies and RNA sequence. These technologies have been used for characterizing genomes, proteomes, and regulatory networks. Seminal findings from the Snyder Laboratory include the discovery that much more of the human genome is transcribed and contains regulatory information that was previously appreciated, and high diversity of transcription factor binding occurs both between and within species. He has also combined different state-of-the-art omics technologies to perform the first longitudinal detailed integrative personalomics profile of person and used this to assess disease risk and monitor disease states for personalized medicine. He is a co-founder of several biotechnology companies, including Protometrics, Affomix, Excelix, and Personalis, and he is presently serving on the board of a number of different companies. Whew, that's a mouthful. Please welcome Michael Snyder.
All right, well, okay, well, good morning, and thanks very much for having me here in that very long introduction. Anyway, I'm going to talk more on the human side, and I'll tie it into a little bit of Frankenstein at the end as well. So we're going to talk about health and medicine and big data. So this is a very popular topic these days, and I'll give you my perspective on it. This is how I think medicine is currently done. When you get sick, you go to a doctor. It's very reactive. That is to say, they treat you after you get ill. We measure very few things, usually a few physiological measurements, maybe a dozen or so, possibly up to 20-ish things and it's done. If you're healthy, you'll go every few years. If you're sick, you'll go quite a bit. What I think we should be doing is focusing on health, keeping people healthy. That should be very proactive. We now have the capability of not just measuring 15 or 20 things, but literally measuring tens of thousands, actually millions of things, as you'll see in a minute. And one could envision doing this frequently, and ultimately I would imagine it, a Safeway or a home test and things like that. So I think this is where, in my mind, medicine should go. And I'll tell you about some of the steps that we're trying to do in this area. Some of this will be personal journey and things we've learned as we've analyzed me in incredible detail, but now actually a cohort of roughly 100 people or so. All right, so what is health? Well, health is actually, obviously, a state you're in. It varies from one person to the next, and it's influenced by many things. It's influenced by your DNA, so obviously your genetic blueprint determines what you will become and to a large extent what you'll look like. But it's influenced by many other things as well, the so-called exposome, the various exposures, meaning pathogens and environmental exposures you may encounter, stresses you may be subjected to, lifestyle things like the food you eat and exercise. We know intuitively these all impact health, but I would argue we're in a position to be able to actually try and understand this much more quantitatively. In the not so distant future, in fact the technology's there, people will be born with their genome already sequenced. And then in conjunction with what types of other information can you get predictive about health outcomes? That is to say, if you're at high risk for Parkinson's, you probably shouldn't be a pesticide worker because with a very high probability that will increase the chances you will get Parkinson's. Now, you may not want to be a pesticide worker anyway, that's a whole different subject, but the point is that if you're high risk of Parkinson's, you especially don't want to be one because that will dramatically increase your probability. So really what we want to do is understand, again, with DNA and these various combinations, how to keep people healthy and at least predict risk for disease. And if someone does get sick, you want to catch that early and obviously get them back to healthy again. Now, I think many of you know there's been a revolution in various technologies, one of which is in DNA sequencing. You can now determine the DNA sequence of a person. So that means determine the order of the chemical structures, the things you just heard Dave talk about. For us, we have 6 billion of those letters all strung in a row, and we can now do this thanks to this revolution in technology. The first genome was sequenced for a cost of around $1 billion. You can now do it for $850. You can determine someone's DNA sequence. There are companies out there that will do this, that will sequence your DNA. Now, what they're not that great at is interpreting that information. We're still at the early days of that. And I would argue most of these companies don't do it very well. There's not that many labs that do it very well. And even still, the labs that do it well aren't nearly as good as we'll be able to do it 20, 30 years from now. Nonetheless, you can get your DNA sequence, and you can at least find certain kinds of very important changes that would be important for your health. We'll talk about some of that later. There's also, this doesn't get as big a splash, but there's been a revolution in mass spectrometers. These are the things in the airport that detect, if you're carrying bomb material as such. They're very sensitive instruments. The ones we use in the lab, they cost about $1 million, but they're incredibly sensitive. They can detect just a few molecules. And as such, you can now measure literally tens of thousands of molecules in blood and urine and actually look at the biochemical composition, if you will, of people in a fairly routine fashion. There's also been a revolution, as you probably appreciate, in wearable devices. We'll talk about that a bit. I don't know how many of you are wearing some sort of wearable device, a smartwatch of some sort. Any folks out there? Quite a few? Come on, this is Silicon Valley. That's it? It's got to be more than that. All right, you have a few more hands went up. All right. Anyway, the point is that there is a revolution, and we think these are going to dramatically change health as well. And things I won't talk about but have a big impact on health, well, now your health records are electronic, and that information's captured, although it's still not organized very well, believe it or not, and even in today's day and age. You can glean a lot of people's health information just by how they interface with email and the internet and things like that. So you can get people's mental state, if you will, by how they write their emails and the websites they're surfing. There are programs to try and predict whether people are depressed or what have you, so that ideally they can tell that before you can. And you can also get people's behavioral information, aggregate that from things like where you're shopping and how you're spending your money and such. You can aggregate all that to try and capture additional information as well. So all these collectively can be brought together to try and at least understand and behavior and people's health, and then try to actually better manage your health. So what we've done is one part of this, like I say, not so much of the last part, and I'm going to talk about some of this today, but we've set up a scheme to be able to look at people in incredible detail that hasn't been possible before. So in addition to, we call this Personalomics profiling, so on an individual level, we follow all these things called omes, and I'll explain what that is in a minute. But basically your genome is your collection of DNA, so we sequence that once. But then we make as many molecular measurements as possible. So this is, I'll talk about this a little bit more in a bit. This is your modified DNA. You can actually get your DNA modified based on lifestyle, the food you eat and exercise. This is all your RNA, that's your proteins. These are a subset of proteins. These are immunoregulators. These are all your metabolites, and you heard about lipids in detail from Dave there. He's a lipidologist, if that's a word. Anyway, you can literally capture all this information at a level that wasn't possible before we follow antibodies. And you may have heard about the microbiome. There are 10 times more cells in and on you that aren't you than are you. These are bacteria. They're very important. They digest your food, keep you healthy, make essential vitamins. We actually capture that from your stool and nasal and wearables I mentioned, and we make standard clinical tests and questionnaires. So we basically would draw blood and urine and actually stool and 6 swabs of people's nose, and we do this on a fairly regular basis. I'll talk about this more in a minute, but basically we'll do this roughly every 3 months, and then during illnesses we'll take many more samples. And the idea is to capture a very detailed profile on people over time, and that over time part is very, very important. So why are we doing all this? Well, we're trying to understand what it means to be healthy on a personal level. That is to say, what does a healthy profile look like? Most people know now what a disease profile, if you have cancer, people study that in incredible detail, but not so much when you're healthy. And so we're trying to understand what does a healthy profile look like, and how does that differ amongst different people? And that's going to be very, very important, as I'll tell you in a minute. We want to understand how individual responses are both similar and different. If I were to throw a common cold virus, say a rhinovirus on this room, many people would get sick, depends on the dose, and they'd have common symptoms like congestion and things, but you'd have very personal ones. Some people get very sick, maybe with headaches and things like that. Others, not so sick at all, and some not at all. So we'd like to understand why people differ like that. Why do some people get sick under certain circumstances, not others? And then as you do this kind of detailed profiling over time, you will learn very, very important things that are important for people's health, and I'll show you examples of that in a minute. Now, as a test guinea pig, some of you may have heard me talk before, we actually tested this out on me first because it was available and I could give lots of blood and it was easy and get the technology. I didn't know I'd be interesting. It turns out everybody we profile is interesting, as you'll see in a minute. So we've been profiling me for about 8 years now. Believe it or not, this next week will be the 8th year anniversary of all this. I've given over 250 now these samplings, these time points where we give lots of samples. And I've been through 11 viral infections, Lyme disease. I actually had a bike accident, woke up in a hospital. I don't go looking for these things, but if they do happen, I might as well get good data out of it. That's how I view all of this. So we can learn something from these adverse events. And this is a general idea. Each one of these is a day. This is just the first, I think, about, let's see, we're through 8. Yeah, it's about the first 6 years of my time course, actually 5 years. And each of these is a common cold. That's a rhinovirus. That's the most common cold. 9 months into the study, had a respiratory syncytial virus infection. That's common in kids, not so common in adults. Anyway, the point out of this is that roughly every 2 to 3 months we'll take blood. There's some before and after trips and things like that. And then when an illness like a viral infection comes along, I'll take many more samples. So you can see as soon as I get congested, I'll take blood that day, next day, 2 days, so on. So dense profiling to try and understand what's going on there is the idea. And then when we get back to healthy every other times. Now I've been doing all kinds of dietary changes. You'll see why in a minute. So I've been doing actually testing to see what happens, the effect of different diets on people's health. You'll see also in a minute that we're doing this on many more people. So just to go through the first part kind of quickly, we sequenced my DNA, which made many predictions, most of which I knew from my family history or health records already. Like I have high cholesterol, and that shows up here with the high lipids. So orange line means I'm at increased risk, blue line's decreased risk. And this is sort of a lifetime risk, if you will. So high lipids, that I knew already. I'm a great responder to statins, and my genome tells me which statins I should and shouldn't use, because some of them could give me adverse side effects. High coronary artery disease. Everyone on my father's side of the family has died of some sort of heart issue. He had 9 brothers and sisters, and so all but one died of a heart, in some cases thought to be coronary artery disease, specifically. Basal cell carcinoma, I didn't know that was in my family history, but then I have 2 brothers, 3 sisters, and when they came out to visit, naturally we took blood from all of them so we could profile them too, so you have to watch if you come visit me. But the point out of all this, we took blood, and I just happened to ask them, well, what do you know about basal cell carcinoma? My genome says I'm at high risk. And it turns out 2 brothers and 1 sister actually had this. So in fact, it was in my family history, I just didn't know it. So I think your genome is a better record of your family history than your family is, because in fact, the information's there. You don't talk about basal cell carcinomas around the dinner table, at least we don't in my family. So anyway, that's something to think about. So one thing that was a big surprise for me was type 2 diabetes. I did not know I had a family history of that. And so one of the molecules we were measuring was glucose, which of course is associated with type 2 diabetes. My glucose had been marching along perfectly normally, but ironically, because of my genome, I went to get what's called an insulin resistance test. It's a very fancy test, and insulin resistance is a precursor to type 2 diabetes. And what you know, when I went in for that test, I had high, what is called fasting glucose. So after not eating, my glucose was high, which is not supposed to be the case. And so we were surprised, measured again, came out high again. A week later, measured it more, went up higher. And this is a measure, you may have heard of this for steady state glucose. It's called a hemoglobin A1C. If you haven't had this, you quite frankly probably should. And it turns out it's arbitrary, but diabetics, 6.5. I was 6.4. I'm right on the edge. So 5 weeks later, I went to my general practitioner who actually looked at me and said, by the way, so did the person who did the insulin resistance. They look at me and say, there's no way you have type 2 diabetes because you don't look it, meaning I'm thin. I was actually even thinner at the time. You don't have family history. There's no way. But in each case, once you know it, so we measured again, even higher glucose, 6.7. I was classified as diabetic. That was April 11th, 2011. I know that because up until then, I had the world's worst diet, ate lemonade and all the stuff because I didn't know how to had an issue, cake. And I cut all that out. I haven't had any of that. I had been biking, but I doubled my biking and I started running, and that's about 8 months to bring it back down to normal. So this made a big deal at the time because it's the first time someone used their genome to predict risk for a disease. In my case, got the disease and got it under control. It was also interesting because when it occurred right after that nasty respiratory syncytial virus, this common cold I told you about before. And so the idea is that I'm genetically predisposed for type 2 diabetes. And in conjunction with this viral infection, that's what triggered the disease. That's the idea. Okay? So hard to prove, but we are testing that now in the study I'm about to tell you about. So the point out of all this is that we think it's genes plus environment. Now you may think this has a happy ending, and it actually, well, it's arbitrary whether you call it happy or not. Some people will say, well, Mike, that high glucose could have gone away on its own, but we accidentally did the right experiment. That is to say, as you'll see in a minute, we've scaled the now study 105 people. And as we're doing that, that's a big project when you're collecting all these samples. And my glucose had been marching along fine, so I kind of stopped looking at it, right? It was looking normal. It's kind of like a Fitbit. Once you get the hang of it, you kind of leave it in your drawer. But the point out of all this is that it was marching along normal. We scaled to 105 people, and I wasn't looking at it. Right around here is when somebody looked at it and said, Mike, your hemoglobin A1C is 7.0. You're diabetic again. And so I had no idea, so I sampled me a few times, started running, it got down to 5.7. That's hemoglobin A1C, by the way, and that's glucose. And so I got it under control, but that was temporary. That's actually several years ago. It's been creeping up since. And I was running about as much as I could, so I tried something different. So there's scientists speaking here, but there's literature that says that actually muscle mass is better for maintaining glucose properly, glucose homeostasis. So you can't tell, but I've been lifting weights for the last 16 months or so. Actually gained a little bit of weight. And actually, it failed miserably. My glucose shot up even faster. In fact, it went to 6.8. And it's been there, it's not temporary, it was there for a while. So 3 weeks ago, I started metformin. It's going back down, actually. So I'm actually a textbook example. Well, the muscle mass thing didn't work, but I respond well to metformin so far. So we'll see how that plays out. So the bottom line out of this is no question I have a glucose control problem. And it also turns out my brothers and sisters are all elevated for hemoglobin A1C too. They're all pre-diabetic, if not diabetic by now. And so we clearly have this running in our family. And I've subsequently learned that 9 out of 10 pre-diabetics don't know it. And I guarantee a bunch of you guys are pre-diabetic for reasons I'll show you in a minute, and you have no idea. And 70% of pre-diabetics will convert to diabetics. So it's a big deal to figure this stuff out now. It's also very easy to do. So this will be one lesson I might throw out to you for better managing your health. The other thing I'll say is genetics is not everything. There's something called epigenetics. Your DNA can get modified, and also the packaging material around the DNA can get modified in very important ways. So it turns out the food you eat, exercise can actually modify your DNA. There's a very cool study out there where they had some people from Sweden, 23 people, biking with one leg but not the other for 3 months, 4 times a week, 45 minutes a shot. And what happened is then they looked at the DNA from the biking leg and the one from the non-biking leg, and there were 4,000 changes. Now, we don't know how that turns into health. This part's still all mysterious. It's an area of active research. But the point out of all this is that actually exercise, and that was done in the muscle, does modify your DNA. and presumably does lead to health consequences in ways we don't understand. We do know that this change in your DNA, it's called DNA methylation, actually does influence gene expression. So it affects which genes are turned on and off. So again, we don't understand how this whole process works, but this is one of these things about how lifestyle does impact your DNA. Okay, so we've actually looked at mine, naturally, for several years to see how mine would change over time. We've looked over the first 3.5 years. And the bottom line is my change in DNA is my DNA changed only twice with this kind of modification. It's called DNA methylation. You can't see, but those are the 2 times when my glucose first went off, and it turns out that's when my DNA changed. So we think that DNA, this modification, actually is heavily affected by chronic conditions like diabetes. It also is affected by aging. Other groups have shown that. And exercise. So we think chronic conditions can change your DNA. And so we think the key is to obviously manage your lifestyle to either avoid those or get them under control. Okay, as I mentioned before, we've now scaled this. We're studying 105 people in incredible detail, just like me, where we follow them every 3 months, and if something adverse happens, like a viral infection or stress or colonoscopy, we'll take many more samples. A lot of our folks are doing dietary studies, and so we're actually trying to understand the effect of diet on people's biochemical profiles, if you will. And what's pretty powerful about this, most people have agreed to make their data completely open, so it's very valuable to the scientific community. I'm going to tell you a few vignettes from this, and then I definitely want to leave time for questions, and I want to see when we're supposed to end here. I think I got it now. All right. So anyway, one thing people say is, well, actually, genome sequencing is a bad thing. What you're doing is really, really bad. If people get their genome sequenced, they're all going to worry a lot. They're going to turn into hypochondriacs, and it's going to lead to millions of dollars of follow-up tests. So we actually tested this idea from 70 of the first folks we sequenced. We asked, first of all, how often do we find pathogenic mutations, and how useful is that information? And it turns out 12 of the 70, it's a minority, but 12 of the 70 have clinically actionable information that comes out of their genome sequence. Just as an example, one individual has a BRCA mutation. You probably heard about BRCA, right? This is a familial mutation, typically familial, where it puts you at very high risk for breast or ovarian cancer. Breast cancer for both males and females, ovarian obviously for females. And the point out of all this is if you have a BRCA mutation, you should either get monitored more frequently, or in some cases people have their breasts and ovaries removed. Angelina Jolie, she had her breasts and ovaries removed, so as a preventative move. And the point out of all this is that there's a number of these that are very actionable, very important mutations. This is an individual that had a mutation, put him at high risk for heart condition called cardiomyopathy. And once you know it, turns out he's a young guy. And then we looked in detail, and sure enough, it turns out he had a heart defect. He's on medication now, all uncovered because of his genome. Let's see. Here's another individual who, this one, we have a lot of our folks you'll see in a minute, pre-diabetic or diabetic. There was a few diabetics in the study. This individual was classified as type 2 diabetic. Turns out he's a different kind of diabetes called MODY. It's not, again, this gets a little esoteric, but it's not that esoteric. The way you treat a MODY person is 100% different from a type 2 diabetic. So he's on the wrong medications, the bottom line, and now switching. So in fact, there's a very famous story of someone who was classified as type 1 diabetic, late in life, learned they're actually this MODY mutation. And so in fact, they estimated they had 21,000 insulin injections over the lifetime. Had they been sequenced at the beginning and saw they were MODY, they would have needed a total of 0 because they were actually getting the wrong treatment. They should have had something else. So the point is that this is a case where you need the right information for the right action and at the right time. So anyway, so at least 3 of these individuals actually have conditions that are consistent with these mutations, and the rest will be on the alert because of this. They'll have tests done when they go to the doctor. And it doesn't lead to millions of dollars. It does lead to a few thousand extra dollars, but obviously we would argue if you catch someone's heart condition early, that's a big deal. So it's a minority of people that's helped, but if you're one of these people, it's a big, big deal. Okay? Other health information is you profile. So we've been doing this for, let's say, for about 4.5 years now. And this is just some of what we've learned. So I mentioned one person with a serious heart issue, another one popped up. One person we caught with early lymphoma and a large spleen as we were doing imaging on them. And they had other markers then as well that are consistent with this. In fact, we found a brand new, we think, biochemical marker that might be a marker for actually lymphoma and possibly other cancers. So again, we caught this early, which means they get treated early. They never would have known it till late had we not been studying them in this incredible detail. Here's a person who had something called a precancer. They have too much of a certain kind of immune cell called IgM cells. And we just, a very young guy, we just were, again, doing our broad scan. Once you know, he had way too many IgM cells. And in fact, so here are two of his time points. Here's everybody else. He's just making way too much. This is a precancer, which 15% probability means it could become aggressive, which could kill him. So we caught this early, which means he'll be monitored for this. And if it starts getting out of control, then there are certain treatments that can be done. I have my own theories of what he should be doing myself. But by the way, I'm not an MD. Disclaimer right here. So you shouldn't take any of my health information, well, take it from my perspective. All right. So anyway, there's all kinds of other things. We had 3 people with serious plaque issues by doing careful imaging of their heart, et cetera, et cetera. There's all kinds of metabolic conditions, and we found them with different assays. So no one assay found everything. That's why we did those comprehensive profiling. But we found quite a few with prediabetes and diabetes. Just to show you this part, this is going into the study. Some of the colors didn't come out right. This is normal here. These are diabetics here, and these are pre-diabetic. This is what people thought coming into our study. Right after we measured them the first time, turns out there were a ton of people who were pre-diabetic who had no idea. And then there were 1 or 2 more diabetics. And as we followed them over time, some people did become diabetic, which we could follow pretty carefully. And many then did take metformin and got under control. Some opted not to, and that's their decision. Okay. All right. So anyway, we would argue this longitudinal profiling is very, very important. The other, I think I'll skip over this. We've learned things too. Some of our folks have done weight gain, weight loss. One of the very interesting things is when you do a study like that, your inflammation pathway goes up when you gain weight. So people gain on average 6.5 pounds. It's kind of like a big Christmas holiday thing where you probably eat too much and then you go back down. The number one pathway is inflammation, and actually your cardiomyopathy pathway gets misregulated as well. So we think there's a molecular explanation for heart attacks that showed up. I want to move into this other area. This will start getting us closer to the Frankenstein theme, I think, which is this wearable space. So many of you may appreciate there are hundreds of wearable and portable health-related devices on the market, maybe over 1,000 now. Kind of lost track. So early on, about 4.5 years ago, we started exploring. At the time, most of these were being used just for, activity monitors, things like Fitbit, right, where you measure your activity, get a sense, and trade your information with other people, and so you can walk the most steps and things like that. We actually got into the space thinking, could we use these for health monitoring? And so the idea was that, maybe these will measure physiology in useful ways, and I'll show you that is in fact the case. So we went out and tested about 30 different devices that we thought were reasonably accurate, and we could get information. It's not always easy to get information back from these devices. If you're a scientist, it's a big deal. We were able to find some. There's all kinds of stuff out there. Ultimately, we settled on 8 or 9 of these that I use every day. In fact, you may notice I'm wearing 3 smartwatches right now. Of other devices, I'm literally wearing 7 measurable things right now. You can't see them all. But they measure all kinds of different things. So they'll measure activity, as we talked about already. They measure heart rate, skin temperature, sleep, blood oxygen, which turns out to be important, we think. Steps, of course. Even radiation. Let me see what Slack radiation levels are here. Hadn't thought to look at that before now. Oh, you're just a touch over Stanford. Not too bad right here. Okay. Whew. All right. Anyway, weight, all these things, well, you can measure all kinds of different things. They actually do relay information into your smartphone. So your smartphone is the collector of all this. It is a pretty sophisticated computer. Oops, there's a piece of paper there. So how do we use this information? Step 1 is to try and find out people's personal baseline levels. And then step 2, as you'll see in a minute, is to try and find deviations from that that might tell you something about health. All right, so here are my circadian patterns. So 24-hour cycle from midnight to next day. This is sleep, heart rate, skin temperature. So I obviously sleep at night, wake during the day, occasional nap, back to sleep at night. Heart rate, low at night, high during day, back down low. Skin temperature, which is different from core temperature, high at night, drops during the day, comes back up, so on and so forth. That's me. This is 43 other people. We've measured many more now. We all have different baseline heart rates, skin temperature, blood oxygen. Everybody's different. In fact, you may not realize that your core temperature, you know how people tell you you're supposed to be 98.6. I guarantee all of you are not 98.6. That ranges from roughly 95, not too many 95s. There's quite a few 96 people, running up to about, say, 100 or so. So that range is actually out there. So if you were to go to a doctor now and your normal temperature is 96, and they measure at 98.6, they say, you're fine, go home. But you're not fine. You're 2.6 degrees higher than you should be. You're sick. So you just gave it. This is why we need these personal measurements so that you're not treated based on the average. You're treated based on you. All right, so anyway, everybody has these different baseline numbers. And then this is activity patterns. So again, we all have different activity patterns. These are monotonic people, not too much movement at night, constant during the day. These are morning people, spike in the morning, morning, afternoon people, morning, afternoon, evening. You can classify people, and you can do this with computer algorithms and group people into different classes. All right. So get people's baseline. Then the next step is deviations from baseline. All right? So this is, in fact, one of my biggest deviations from baseline. This is known already, but your blood oxygen drops on airline flights. Okay? So here is a trip from San Francisco to San Diego. Green is altitude. Plane goes up, comes down. Here's my blood oxygen. Starts high, goes low where the cabin pressure gets normal, and comes back up when I land. Okay? What's not so well documented is how low does it go and how long does it stay low? And the answer is, this number is still pretty accurate, about 5% of the flight. It'll be 90 or below. And we think this is now an underestimate, depends on the planes and such. By the way, you can tell the actual air pressure with an app on your iPhones. And I now have this information. I didn't have it when we first did this study, but you can know exactly the air pressure. And they're not the same. I can tell you, just came back on a 757. Those are always better pressurized than the 737s. Okay, we'll pull all that data together soon, so stay tuned for the actual numbers. But the point is that this stuff is all out there. You can collect it, so you guys can be citizen scientists and collect it as well. Anyway, it turns out at least 70% of the flights, 96 or below. I actually think that number is higher, but let's stay with that 70%. Keep dropping things here. All right, so that was me. We've done this on lots of other people. Everybody, with one exception, drops in an airplane. Their blood oxygen drops. Okay, that will be true for all ethnic groups, and we've tested all common ethnic groups. That's certainly the case. All right, so your blood oxygen drops. Your baseline will differ, but you'll still drop. All right, so what you also won't find out there, what does it mean? Well, it turns out it correlates with fatigue. So that is to say, you can do a blinded test to see whether you're alert in red, this is me, or tired in blue. So you say whether you're alert or tired, and then see what your blood oxygen is. And so for me, that number is 96. So generally when I'm 96 or below, I'm tired. And on 96 or above, I'm alert. You can also do reaction time tests, meaning how quickly can you see and react to a visual cue. Do that blinded, and of course your reaction time is faster when your blood oxygen's up. It's all measured on an airplane. You can measure it on the ground, same thing's true too. So the point out of all this is that we think the reason then you're tired on airplanes isn't because you've been working too hard or having too much fun staying up too late. It's because the air pressure's low and your blood oxygen drops, okay? That's the correlation. All right, so if you're a workaholic, that's super disappointing, but there is hope for those of you who travel long distances. So it turns out you can adapt on long flights. So for me, that number is 7 hours. So as I say, here's from Frankfurt to San Francisco. My blood oxygen drops initially, but we've done this on many flights. Pretty much always comes back up after about 7 hours. I don't know how much that varies with other people. So if you're a workaholic, hang in there because you may actually be able to get some work done on the end of the flight you weren't able to do at the beginning. So why is all this important? Well, again, that's amusing, of course, but from a health standpoint, it turns out we think these will be valuable sensors for health. And in fact, the smartwatch helped me detect when I had Lyme disease. First detected because of my smartwatch, actually. And this is picked up on an airline flight I was actually flying to Norway through Frankfurt. And on the short flight, because I measure myself all the time, that's what my blood oxygen should look like on a short flight. Drops a little bit, comes back up. On this flight, the median was 90, and when I landed, it never came back up. Okay? So my blood oxygen was abnormally low. I looked at my smartwatch, and wouldn't you know it, it was running high. My heart rate was running high, and I later learned my skin temperature was high. So these are daily measurements of heart rate. And I forgot to say, I have plenty of time then, good. So I forgot to say the backstory behind this is I was helping my brother put up fences in rural Massachusetts where 55% of ticks are Lyme infested. And then basically, 2 weeks later is when I was doing this trip to Norway, and again on the second leg, my blood oxygen was way too low, my heart rate was running way too high. I knew something wasn't quite right because I measure myself all the time. I knew it wasn't jet lag. And so then after I got there, I did get a low-grade fever. I went to a doctor in Norway who basically drew blood and said, yep, your monocytes are up, well, these are immune cells, and so you have a bacterial infection. I said, oh, yeah, and he said, you should take penicillin. And I said, no, I should take doxycycline, which is what you use for Lyme disease. As you might imagine, things are pretty tense for a few moments there because physicians don't exactly like to be told from their patients what they should be taking. So he reluctantly gave in, gave me doxycycline, cleared up 24 hours later. So I took it that day, cleared up by the next day. When I got back, I actually gave blood in a test, and I was Lyme positive for both the antibodies, and there were even some antigens hanging around. And I had the perfect control because I had given blood before I left, and it was negative. So there's no question that it wasn't a false positive test or anything like that. I clearly had gotten Lyme disease, and it manifested itself as it progressed. So the point out of all this is that this was all first detected with my smartwatch. It's a very simple smartwatch. That led us to write algorithms. Let me back up. Then we looked over 2 years of data I had where I had 2 known viral infections, and I had been measuring something that measures infections called CRP, if you've ever heard of it, C-reactive protein. It tells you whether you're sick or not. So we looked back over those days. These are outlying heart rates and outlying skin temperature, and there were 4 periods where I had outlying measurements. One was the Lyme disease I mentioned before. You can't miss those signals. They're really strong. Your heart rate is not good under those circumstances. And there were 2 viral infections, one here and one here. And there was a third time I didn't report being sick, but wouldn't you know, I had this high CRP, which says I was sick, I just didn't report being symptomatic. So the point out of all this is that every single time I was sick and either knew it or didn't, actually my heart rate and skin temperature was up. So that led us right, and the other times, I measured myself 70 some other times, and it was all much lower. So we then wrote an algorithm to be able to tell when you're getting sick before you realize it. Okay, basically you're looking for elevated heart rate over your resting heart rate. And now we can do it, we think, even if you're walking. And so the bottom line out of all this is over the 4 periods of this is kind of a change in heart rate. It's a little complicated. But these are the times when I reported being sick at these red lines. But much earlier, you can see this change at that little triangle, this change, before you actually report being symptomatic. And this algorithm not only works on me, the heart rate's better than skin temperature. It works on 3 other people who got sick, one of whom got sick twice. And the point out of all this is that we think your heart rate goes up. Again, before you realize you're sick, you might start feeling a little something. But we can detect it with a simple smartwatch. So we're now trying to, as soon as we get IRB clearance, it seemed to take forever, we're going to roll this out to thousands of people and see if we can test this out. So tell whether you're getting sick as well, okay, just from your heart rate. I got behind, so I won't have time to tell you about this, but we actually think you can tell early signs of diabetes, this insulin resistance, from your smartwatch as well. Your heart rate's a little bit different, your daily heart rate, than it is if you're insulin sensitive. So in the early forms of diabetes, and there are also glucose monitors. That's a little more invasive, but you can use those too. They're more definitive. So the point out of all this, we think there are many measurements for being able to detect this. Where this is all going, well, we think your smartphone is in fact going to be your command center for your health. All this information relays in. We're actually building personal dashboards, health dashboards for this to be able to collect all the wearable information, microbiome, all this information, and display it on your smartphone, very much like your car dashboard, so you can actually follow your health actively. This should be shareable with your physician so that they can look at it as well and be able to follow your health parameters as well. Lastly, I'll just say we're not just limited to following what's inside the body. We are actually setting up devices. I won't have time, but I'm happy to talk to anyone here. We can measure now exposure information, both for biologicals and chemicals. And I carry this with me all the time, so you can follow it actually in semi-real time. So you can see what your exposures are, which is a big deal if you have allergies and asthma. So this is a future I envision. We're going to be in a world not so far away where people will get their genome sequenced before they're born. Then with these other biochemical and wearable measurements, we can actually now predict risk early, catch disease, and be able to manage people's health much, much better. So how does this tie into Frankenstein? Well, I think Mary Shelley, great story, had it all wrong. Trying to put together a person from parts, I actually think we're going to do the opposite. I think we're going to start with a human and layer all these mechanicals on them that will actually be able to better follow their health, possibly replace parts that may be getting a bit worn out, and then be able to manage people's health that way. So it's a flip side of this whole thing. So I'm very fortunate. I have an amazing lab that's helped actually execute all this work. And here's a shameless plug for a book I wrote a little time ago. And if you're interested in this space, feel free to take a look at it. So thanks again.
So if there is one thing that we should buy to monitor our health, what should it be?
Well, I think a smartwatch, but the smartwatch we like the best they pulled from the market, but I would still get a smartwatch.
Okay. We have time for one question. Quick question. Yes.
That was a wonderful talk. I really appreciate it. One of the things you said is that, if I got it right, is that what I do on the internet and where I go shopping, that they might know I'm depressed. Who's the they?
Well, right now, hopefully, certain people are following your internet, right? You do know that Google and Yahoo have all your information about your internet behavior. That's why you're getting ads tailored to you.
Does that include Cambridge Analytica?
Functions. What's that? Oh, I missed what you said? Cambridge Analytica. Cambridge Analytica, yeah. Well, I don't know what to, I think we do need protection rules for how that information would be used. Obviously, this can be used to your advantage, and that's what we all want. When it's used to your disadvantage, we want to be able to avoid that. So, yeah. So if that's all, I'm happy to stick around.
Yes, we're going to have a break right now, and we're going to reconvene at 12 o'clock. So if you have questions, please ask the speakers.